are jumping into first grade, and we need to build on everything that we learned in kindergarten and ideally continue expanding those ideas and concepts and ways of counting into first grade. So we're still going to be using manipulatives. So we're going to cover clusters with operations in algebraic thinking and number and operations in base 10. So operations in algebraic thinking, there is a lot of different groupings here. So be patient as we go through them. We're going to try to hit on each and individual specific standard as we go along. So some common manipulatives that we will use are objects for counting. Those can be the counting bears, it could be chips, it could be anything that you can count with. 10 frames, double 10 frames, because we need to count above 10. As you see, we need to use addition and subtraction within 20. Also, we're going to use a hundreds chart, dot cards, numeral cards, number line to 20, an open number line, part whole chart, place value chart, various dice, and various spinners to do all of these items. So let's get to it here. Let's say that Allie had 9 marbles and Maria had 5 marbles. How many more marbles did Allie have than Maria? So I'm going to use marbles as counters. So I placed 9 counters for Allie, and we can count them 1, 2, 3, 4, 5, 6, 7, 8, and 9. And Maria had 5 marbles, so 1, 2, 3, 4, 5. How many more marbles did Allie have than Maria? Well, I can see if we were to partition them off that the group that's hanging over is the more amount that Allie has. So this is a difference unknown problem. We see that Allie had 4 more marbles than Maria, so 5 plus how many gives us 9. Similarly, a different way to write this is Allie had 9 marbles, Maria had 5 marbles, so the same setup. How many fewer marbles did Maria have than Allie? This is still a difference unknown problem. We still see that Allie has 4 more marbles, but the way we write this problem based on what the information is given is 9 minus 5 is how many. So just different way of writing it. Allie had 4 more marbles than Maria. Maria had 5 marbles. How many marbles did Allie have? So again, we're going to use our counters. So I start with Maria having 5 marbles. And if I know that Allie has 4 more marbles than Maria, I know that she at least has 5 of them. But then we need to add 4 more to have 4 more than Maria. So this is a bigger unknown problem. So Allie had 9 marbles, so 5 plus 4 equals how many? And so we would see that there's 9. Maria had 4 fewer marbles than Allie. Maria had 5 marbles. How many marbles did Allie have? So again, we have our counters. So if we start knowing that Maria had 5 marbles to begin with, and that would mean Allie had 5 marbles to begin with as well, but Maria had 4 fewer. So we would want to know what minus 4 would give us 5 marbles. So we know that that would be 9 minus 4 is 5. Another way of writing a bigger unknown problem. Allie had 4 more marbles than Maria. Allie had 9 marbles. How many marbles did Maria have? So starting, we know that Allie had 9 marbles to start with. We know that Allie had 4 more marbles than Maria. So I left like a blank space there to indicate that those 4 marbles are the 4 more than Maria, what she had. Maria had 5 marbles. So what plus 4 gives us 9? This is a smaller unknown problem. Maria had 4 fewer marbles than Allie. Allie had 9 marbles. How many marbles did Maria have? So we have our counters again. This time it's a little backwards because we know that Allie has 9 marbles And we know that Maria had 4 fewer than Allie. So I'm leaving a gap there of the fewer piece. So 9 minus 4 is how many? Maria had 5 marbles. Another way of writing a smaller unknown problem. So we just covered 3 types of comparison problems using the same numbers just written in different ways. So those with an unknown difference and 2 known numbers, those with a known difference and a bigger unknown number, and those with a known difference and smaller unknown number. Each of these can be solved using a variety of addition and or subtraction, and you can see it with slight differences in language. Another great way to have used and use this would have been to use a number line. So let's consider the tens frames. 5 plus 3 is 8, and 3 plus 5 is 8. So I've got my tens frames here. I've got 5 on the top row and 3 on the bottom, or I've got 3 on the top, and then I continue along that top row, giving me 5 more counters. What if we did the same addition using a number line? So here I have 2 different number lines. I start with 5, and then I jump 3. Or I start with 3 and then I jump 5. We can see in either instance that no matter which one we jump first, we get to 8. What if we did the same with bear counters? I have 5 bears and I add 3, or I have 3 green bears and I add 5. I still see that altogether I have a total of 8 bears. So when we look at the dots, the number line, and the bears, what do we notice about all of them together? Well, we see that no matter what type of objects we use to count, we still get to 8. What do you notice about the add-ins in these problems? So add-ins are the numbers that we're adding together. 5 and 3 are the add-ins. What do you notice about the total? Well, we see it's always the same. I would encourage you to use other counters and use different add-ins, such as 2 and 3. Would the results still be the same? Well, it's 2 plus 3 is 5, or 3 plus 2 is 5. Do you think this will always be true? This is known as the commutative property. So it doesn't matter which order we add in, the result is still the same. We can extend this idea with 3 or more add-ins using 10-frame, number lines, or counters. So on the top there, I have added 7 plus 3 plus 6. And on the bottom, I've added 7 plus 6 plus 3. So it doesn't matter which order we add in, the property will always be the same. So this is the associative property. It's a direct extension of the commutative property, only we have more than 2 numbers that we're adding together. Using a part-whole model to help make the connection between addition and subtraction. So I've put some counters in the different pieces of the part-whole. So on the bottom are our parts and the top of each one is our whole. So when I start at this first box on the top left here, I see on the left side I've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. So if I were to count them all together, I should get 12. But I think I have 1 too many, so let's get rid of 1. Yeah, let's get rid of 1 so that it matches. 1 too many of them, I apologize. So then we can put in our box here that we have 12 altogether. Moving on to the next, I see I have 1, 2, 3, 4, 5, 6, 7, 8 parts, plus how many parts would get us to 12? Well, we would know that we would need to put 4 here. Similarly, I know that the whole needs to be 12. Part of it is 4, so then we would need another 8 to reach the whole part of 12. Let's get rid of this one. Okay. So what we are modeling in the first one is addend plus addend equals total. The second box is addend plus missing addend. We don't know the second part equals total. Or we could rewrite it as a subtraction as total minus addend. So 12 minus 8 gives us the missing addend. Similarly, on the last box, they're interchangeable depending upon which numbers are there, but addend plus missing addend equals total, or total minus addend equals missing addend. So part wholes are great for showing difference and subtraction and addition. Let's compare the number of circles in each box. If they are equal, write a number sentence. If they are not equal, write not equal. So the first set of boxes I see I have 3 plus 2 plus 1, and the second box I have 3 plus 3. If I were to count them individually, I have got 1, 2, 3, 4, 5, 6 in the first box. And on the second box, I have 1, 2, 3, 4, 5, 6. So I see that they are indeed equal to one another. The second set of boxes, I have 1, 2, 3 plus 2 plus 3 plus 3. These are in fact not equal, because on the left we've got 5 dots, and on the right I see I have 6. Which leads us into ways and strategies for counting. So I've got some counting techniques that are developed in kindergarten, and we're going to further develop these into first grade. So on the left, I've got counting all. This would be when we're using addition. So we would start with 1 and counting to find the total number of objects. So if I had 8 plus 4, we would start from 1, count up to 8. 1, 2, 3, 4, 5, 6, 7, 8, and count up 4 more, which typically is done with our fingers or using physical objects. So 9, 10, 11, 12. The counting on version, we count from the start number rather than starting at 1. So the same number combination, 8 plus 4, we would start at 8 and then count with our fingers 4 more, 9, 10, 11, 12. Or we could count all with subtraction. So we would remove the appropriate number of items. So we would have physical objects with us and count the remaining items starting with 1. So if I start with 12 counters, I need to remove 8 of them. So I would count out 8 to remove them. And I would see I had 1, 2, 3, 4 objects that are left. Or a little bit more sophisticated, we could count back. Start with the total and count back the number of being subtracted. So start with 8 and count back 8, one number at a time. And you could use your fingers to keep track of 8 spaces as you're going backwards. Count on with subtraction. Start with the change number and count on to reach the total. So start with 8 and count up to 12 by ones. And of course, when we get more sophisticated, larger numbers. So 8, 9, 10, 11, 12. I see that there were 4 spaces to get to 12. So some counting strategies that we learned in kindergarten, we are going to move them more sophisticated in the first grade. So if I looked at 5 plus 6, this could be considered as doubles plus 1. So we're decomposing the number 6 into 5 plus 1. So then 5 plus 5 we know is 10, plus 1 more is 11. Similarly, we could do doubles minus 1. So I could decompose 5 as 6 minus 1, knowing that the doubles, 6 plus 6 is 12, subtract 1. So more mental computation. I could make 10, decompose 4 into 3 plus 1, since I know that 7 plus 3 is 10, plus 1 more is 11. We could make 10, decompose 3. I need 2 more to get to 10, so 3 is 2 plus 1, which is 8 plus 2 plus 1. Count on 2 or make a 10. So I could decompose 2 into 1 plus 1 because I need 1 more to get to 10 with 9, or count on 9, 10, 11. And then here, just count on 1. So 10, 11. Okay, moving to number and operations in base 10. So now we're going to extend counting to 120. And we can pick up at any place in between to get to 120. Understand place value. So knowing that we can bundle 10 units into a group of 10. Use place value, understand properties of operations to add and subtract using 2-digit numbers. We can use number charts to develop all sorts of number senses. And even though the number chart I'm going to show you ends at 100, you could easily do these same items all the way up to 120. So let's go over them. The first one I'm going to show you is that all the numbers in each column have the same number in the ones place. So I've got this column here done, and I see that all the numbers have 2s in the ones place. So if I went to the next, all the ones 4s. Okay. Similarly, let's go on the rows. If I choose the row all the tens digits in, well, to there I should say, all the tens digits are the same. You can also talk about reversed numbers. So if I had 17, the reverse number is 1, or 48 and 84, or 90 and 9. So that students understand that place is important, where it's located. 12 and 21. Also great to talk about numbers that come before or after. So if I slap 48, 1 more than 48 gives me 49. Or if we look at the number before the number that precedes 48, 47 is 1 less. We could further instigate that 10 more than 48 is 58, and 10 less than 48 is 38. So we can develop a number sense around an individual number based on the numbers that are around it. Count by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, etc. And students will begin to see that when they're counting, it creates a nice pattern in our hundreds chart, which you can extend to 150 as well. We can also count by 5s. 5, 10, 15, 20, 5, 30, 35, 40. And students will again are starting to see a pattern where these numbers fall. We can also count by 10s, 10, 20, 30. Again, finding a pattern of where these numbers fall with one another. So we learned in kindergarten that if we had a group of 10 ones, we could group them together and make one group of 10 and 0 ones. So I've got some base 10 pieces here. I've got 10 individual units on the left, and I'm going to group them into what we call a long or a group of 10 for now. We can extend this idea using the place value chart. So I've put my 10 ones into the ones column here. And I'm going to circle them because I have 10 of them and move that 10 into the tens column and create an individual long or group of 10. How could we represent 34 units using tens and ones? So imagine I have 34 units hanging around just randomly. I can start grouping them into groups of 10. So I would be able to create 3 groups of 10 with 4 units left over. We have 3 tens and 4 ones, which represents the number 34. Once students get a feel for place value of tens and ones, they begin to naturally compare two numbers by looking at the number of tens and ones in each number. Beginning with concrete materials such as the place value chart or a number line, they'll be able to generalize that the number with the most tens is greater, and if they have the same amount of tens, the number with more ones is greater. So let's identify which is greater, 47 or 32. So I've got my place value chart. I'll have one chart for each item. I know that with 47, I'll have 4 tens and 7 ones. And 32 is 3 tens and 2 ones. 47 is more than 32 because 47 has 4 tens, which is more than 3 tens in 32. Which has fewer, 25 or 28? So we've got our place value chart, and I know that there are 2 tens in 25 and 5 ones in 25. I know that there are 2 tens in 28 and 8 ones. I know that 25 is less than 25 because they both have 2 tens, but 5 ones in 25 is less than 8 ones in 28. Using concrete models to develop and understand addition helps students generalize beyond basic facts and are able to progress to making generalizations and develop their own strategies. So let's show 23 plus 6 using base 10 pieces. So 23 is 2 tens and 3 ones, and 6 by itself is just 6 ones. I count that I have 1, 2, 3, 4, 5, 6, 7, 8, 9 ones, so I do not have enough to regroup and make into tens. So 23 plus 6 is 29. I see that I don't have enough ones to regroup into a group of tens, so I still have 2 tens, and now I have 9 ones, so 29. You give this one a try. Show using base 10 pieces that 33 plus 50. Pause the video and only start it when you figured it out. So 33 is 3 tens and 3 ones, and 50 is 5 tens and 0 ones. I don't have enough ones to regroup, so I have 8 tens and 3 ones to make 83. Show using base 10 pieces 35 plus 7. 35 is 3 tens and 5 ones, and 7 is 7 ones by itself. Aha, I see that I have enough ones to make a 10. So I'm going to group together 10 ones to make a group of 10, which then leaves me with 4 tens and 2 ones. So I started with 3 tens in 12 units. I regrouped 10 units to make a 10, which gave me now 4 tens and 2 units, so 42.